Hi, I'm going to go over lesson 4 on proving the area of a circular region, or a circle, for those of you that weren't in class today. You have the notes, or you can download the notes from Canvas. So here we are. I may stop from time to time to allow you to do a little bit of the math work. And the first thing we're going to do is look at, oh, by the way, up here, let's see, I've got to get used to my tools. Right here, there's a video that you can go look on your own if you want to copy and paste that, or just type it in, I guess. You can go and look at the proof of the formula for the area of a circle. It's a short video and it's kind of neat to take a look at. But the first thing other than that I'd like to do with you is take a look at right here, number 1. The area of a regular hexagon inscribed in the circle that we have over here. In the diagram to the right, a regular hexagon, regular being all sides congruent and all angles congruent, has been inscribed inside a circle C with radius R. So over here we have the radius, follow the pen, radius R, the center is C. Notice the altitude is H, the altitude of this triangle. One side of the hexagon is S. Back over here to A. Each subregion of the regular hexagon is A. When they say subregion, they're referring to this triangle over here. Notice the hexagon was broken up into 1, 2, 3, 4, 5, 6 subregions, as they call it, or 6 triangles. So, what kind of triangles are those? If you said equilateral triangles, you are right. So fill that in. And I'm going to mark it. I'm going to mark it down on this one, that each of these sides is congruent. That also means that this angle here is going to be 60, and here will be 60 degrees, and this will be 60 degrees. Remember also that when the vertex angle is 60 up here, and we drop an altitude, that divides the vertex angle into 2 congruent angles. So this angle here will be 30. This one will also be 30. So down here or up here, we'll have a 30, 60, 90 right triangle. That's going to be important to us when we start solving some problems a little bit later. Moving down to question B, or problem part B. Determine the area of each subregion, that would be each equilateral triangle, in terms of S and H. Looking over at the picture to the right, we want to determine the area of this equilateral triangle. One subregion being one equilateral triangle using H and S. Well, knowing that the formula of a triangle is 1/2 base times height, we're just going to substitute S and H. So, area of that triangle will be, area is 1/2 base, which is S, times height, which is H. 1/2 S times H. That was not bad. Down here, use your answer in part B to determine the area of the regular hexagon. Well, we discussed earlier that each of these triangles was the same. They're all congruent, and there are 6 of them. So if the area of one of them is 1/2 SH, then we would just multiply that by 6 to get the entire regular hexagon. So the area of the regular hexagon would be 6 times 1/2 S times H. Now I'm not going to reduce the 6 and 1/2. I normally would, but for a certain reason I'm not going to do that yet. Down here, with regrouping we get the following. By regrouping, what I mean is, I'm going to take a look back at the diagram, and I'm going to notice something. combine the 6 and the s. 6 times s. I just rearrange it. 6 times s times h times 1/2 times h. So I just took these and I rearranged them. Regrouping, rearranging. What is 6s with regards to this diagram? There's s, and now I'm saying I have 6 of them. 1, 2, 3, 4, 5, 6. You're right. That's the perimeter. 6s equals the perimeter. I'm now going to replace the 6s with the word perimeter. Therefore, the formula will be the area equals, take this 6s, which was this formula rewritten, and replace it with perimeter times 1/2 the height. And there you have the formula for the regular hexagon, for the area of the regular hexagon. There we go. Okay, we're not going to look at number 2. We're going to move to the next page. Over here. So what this packet is really all about is estimating the area of a circle. We already know how to find the area of a circle. To find the area of a circle, we just use pi r squared. And if you looked at the video, I'm not sure you did yet, the video developed the area formula for the circle. We know how to find the area of a circle. But in this packet, in this lesson, we're going to talk about how to estimate the area of a circle using regular polygons. Inscribed and circumscribed. So in here, right now, I'm going to ask you, on this left circle, to inscribe a regular hexagon. Just like it says up here. I think it says it above here. Okay. Well, we're going to inscribe it. It may not say it there, but we're going to inscribe as best as you can. I'm going to freehand it as well. I'm going to go across. 1, 2, 3. This may not look so regular. 4, 5, 6. Okay, not the best job. I think I can do better. I'll let you attempt that while I attempt to do better as well. I need to do a much better job of a regular hexagon here. So I'm going to go here, here, here. Okay, it's a little bit better. It doesn't really quite look regular, but it looks like they're even anyway. So I inscribed a hexagon. It doesn't quite look regular. Do the best you can to make a regular hexagon. And then we're going to inscribe a regular octagon on the right, or circumscribe an octagon on the right. To do that, we need to go across, down, so you touch it there, down on the side, down adjacent to this side of the circle, and across, and you touch the bottom, up adjacent to that side, and then up, so you touch the side, and then across. Okay, that really wasn't so good either, but I'm doing my best. You can try that yourself. I'm going to fix this side over here. Extend this one a little bit and then go down right. And then we come down this way. Okay, not the best octagon, but I drew an octagon that's circumscribed. So we have an inscribed hexagon and a circumscribed octagon. My point for doing this is I'm going to ask you a couple questions to think about. If we inscribe a polygon inside the circle, it takes up a portion of the area. Think about what would happen if I continue to increase the number of sides of the polygon. Right now we have 6 sides. What would happen if I made an 8-sided polygon or a 9-sided polygon? What about a 12-sided? What's going to happen if I keep increasing the number of sides? what will happen to the area of the polygon? What will happen to the shape of the polygon? So as we increase the number of sides, what happens to the area of the polygon? Area of the polygon, increase it, the area of the polygon gets larger, and the shape of the polygon gets more circular. So let's go back up here and answer these questions. How do the areas of the inscribed regular n-gons compare with one another as n, the number of sides, increases? An n-gon is just a polygon of n sides, n being any number. So the area of an n-gon compared to the n plus 1 gon. For instance, a 5-sided figure compared to an 8-sided figure, or a 10-sided figure compared to a 12-sided figure. That's what we're just considering if I have the 5-sided figure compared to when I make a 10-sided figure. Well, we said the area increases with the number of sides, so the n-gon's area will be less than the area of the n plus 1 gon. How does the area of the inscribed n-gon compare to the area of the circle? Well, no matter how big this n-gon gets, it's never going to reach the area of the circle. It will always be less than the area of the circle. Moving over to here, considering the circumscribed polygon, we're going to answer some questions. How do the areas of the circumscribed n-gons compare with one another as the number of sides increases? So the area of the circumscribed n-gon has compared to the next n-gon. So we're talking about up here. As you increase the number of sides, remember the same shape applies. As you increase this shape, as you increase the number of sides, the shape is still going to become more circular. So over here, as I increase the number of sides, that blue figure is going to become more circular. So think about that. It means that that blue shape is going to wrap more closely around the circle. So what will happen to its area? For instance, a 10-sided figure compared to a 12-sided figure, which wraps more closely around the circle, this is going to have more area. And the area of the n-gon compared to the area of the circle, the n-gon's outside. It's larger. It's shrinking closer and closer to the circle, but it's still larger. Writing an extended inequality which shows the relationship between the area of two regular n-gons, the inscribed, the circumscribed, and the area of the circle. Well, what's the smallest one? Starting from the inside, we have the n-gon was less than the circle the area of the n-gon, which was less than, what was it less than? The inscribed polygon is always smaller than the circle, which was always less than the circumscribed polygon. So it might seem very advanced. Basically, if you look at this diagram right here, we have this circle in red, and we have two polygons, an inscribed polygon in blue, and the other, the circumscribed polygon in blue on the outside. This is trying to show you that the circle which is between them is the circle lying between them and the two polygons, one outside, one inside. As we increase the number of sides on those two polygons, the circumscribed gets closer to the circle, and the inscribed gets closer to the circle as the number of sides grow. So to estimate the circle, we would just circumscribe the polygon and inscribe the polygon, and they would get, the more sides I have, the closer the estimate gets to the circle. And that's what we're going to do in this lesson. Down here to F, we're going to skip E and D. We're going to go to F. The areas of the inscribed polygons get inscribed. We're talking about inscribed. Get larger, but never larger than the area of the circle. Never greater than area of the circle. The areas of the circumscribed polygons, those are the ones on the outside, get smaller, but never less than the area of the circle. Circle is the limit. How large would n have to be in order for the area of the inscribed n-gon or the circumscribed n-gon to be equal to the area of the circle? How many sides would the polygon have to have? Remember, as the sides increase, the polygon becomes more circular. I have to go to infinity. That polygon will never actually reach being a circle. And that brings us to a topic from pre-calc, calculus. The limit as n, the number of sides, approaches infinity. So as the number of sides gets closer and closer to infinity, the area of the inscribed n-gon will be equal to the area of the circle. So as n goes to infinity, it's going to reach the area of the circle eventually. Well, you'd have to get to infinity. We have two important formulas we're going to be using. One we already know, the area of the circle. And this one we just went over today, that the area of a regular n-gon, that's now for any regular polygon. The area of a regular n-gon is the perimeter of the n-gon times the height divided by 2. New formula. Well, if you want to take a break now, you can. This is what we did the first day. This is where we stopped the first day. And on the second day, we went to the next page. It's been a long video so far. I've given you a lot of information. Feel free to take a break, because the next day of the lesson went to the next page. Now moving on, because if you're up for it and ready for it, let's go attack some problems using what we just learned. On this page, we're going to approximate the area, what they call a disk, a circle, using the inscribed hexagon, the circumscribed hexagon. Then in question 3, we're going to take the average of those two, and then we're going to find the actual area of the circle in 4. Well, we're going to find the radius. We're going to step through it. There's more questions on the next page, but eventually we're going to find the actual and compare it to our estimate. Here are number 1, approximate the area of a disk or circle of radius 2 using an inscribed regular hexagon. Here's the radius. Notice in this question, the radius goes to the center out to a point on the circle. And in this case, the radius is one of the sides of the equilateral triangle. We said before we were going to have a 30, 60, 90 right triangle in these pictures with the regular hexagons. And they've already actually labeled the sides for us. We end up with a 1, 2, right, 3. So this is our standard 1, 3 goes from 60 and 2. And they've labeled the sides. So the area, remember the area formula, area is 1/2 times perimeter times the height. Let's fill that in. Area is 1/2. The perimeter is going to be, well, let me change colors now. I need this full side length. This piece here is 1. That makes this entire side 2. The perimeter would be, this is 2, and there's 6 of those. 2 times 6 would be 12. I got the perimeter because 2, 2, 2, 2, 2, 2. Perimeter equals 2 times 6, which is 12. Times that by the height, height being the altitude, from the vertex down right there, and that's radical 3. This is radical 3. It's not as bad as you think. So from here, I'll have half of 12 is 6, and I'll get 6 radical 3 square units. That's my first approximation. It's the approximation using the inscribed hexagon. Moving down to approximate the area using circumscribed regular hexagon. Notice again the radius is 2, except that in this diagram, look at the radius. It goes from the center out to the, oh, that's not it. Notice, that was in the last one. Is that the radius? No, because the radius goes out to the circle. It's not the same. We have to be more careful in this one. A little different. Radius goes from the center to a point on the circle. So in this one, we have to drop an altitude. These are very different questions. With the inscribed, it's a little easier because we use one of the sides of the equilateral triangle. For this one, we have to make our own radius. We have to drop an altitude, making again our 30, 60, 90 right triangle, knowing that the radius is 2. That's the radius here. Write down our 30, 60, 90. Across from 60 is the 2. That's the 1. That's the radical. Which radical? Remember your ratio? Very good. Radical 3, 2. They gave us across from 60 as 2. Do that in purple. They gave us a 2 here. To go from the middle leg to the short side, I divide by radical 3. I'm going to go over here. 2 divided by radical 3. You cannot leave a radical in the denominator. Remember how to do that? You need to rationalize it. That's right. You've got to multiply by radical 3 over radical 3, which gives you 2 radical 3 over 3. That belongs right here. And in case we need it, I have to take this length and double it to get across from 90. When I double this, that means timesing it by 2. I just multiply those to get 4 radical 3 over 3. What did I actually need here? Well, to find the area, I need perimeter times height divided by 2. For perimeter, I need this full length times the height which I have divided by 2. I need this length, which means I need the side across from 30, but 2 of them. Side across from 30 times 2, which I've already done. So I need 4 radical 3 over 3. So the area will equal, we need to take this 2 radical 3 over 3, which represents this piece here, and we need to double it to equal one side. So that's going to be 4 radical 3 over 3. I need to get the perimeter, so I take this and multiply it by 6. There's my perimeter times the height of 2. So I have the perimeter times the height. And then I need to divide by 2. So what's going to happen is 3 cancels 6 twice. The multiply by 2 and divide by 2 cancels. And when I multiply these, I'll get area is equal to 8 radical 3. There we go. In question 3, based on the areas of the inscribed and circumscribed hexagons, what is an approximate area of the given disk. Then, what is the area of the disk by the area formula, and how does your approximation compare? So over here, we're going to do an estimate using what we did with the hexagons, and over here, we'll do the actual by formula using pi r squared. Oh, this is the easier one, of course. So if the radius is 2, our actual is going to be 4 pi. The estimate, the two numbers we had were 6 radical 3 and 8 radical 3. So to take the average of those, I would take 6 radical 3 plus 8 radical 3 and divide them by 2. So that gives me 14 radical 3 divided by 2, and that's 7 radical 3. Now to compare these, I need to get my calculator. And here's my calculator. 7 radical 3 gives me approximately 12.12. And over here, using the calculator for 4 pi, I get approximately 12.57. What is the radius of the circle whose circumference is pi? Well, before I get to question 2, notice how close we came with the areas. This was our estimate, and this is the actual. We're not so far off. We did pretty well. And that just goes to show you that when you do the estimates using the inscribed and circumscribed hexagons or polygons, you can get fairly close. And I'm sure if we used an n-gon with more sides, we would get even closer. I'm going to do one more question, and then I think you're good to go on your own. This question is short. The circumference is pi. You remember, cherry pie is delicious. So, cherry pie is delicious. The circumference is made of pi times diameter. They gave us the circumference as pi. I'm going to substitute that right here. Pi equals pi times the diameter. If you solve that for the diameter by dividing by pi, divide by pi, this becomes 1. Therefore, the diameter is 1. We need the radius. The radius is half the diameter. So the radius is 1/2. Done. That's it. On the next page, we're back to some problems that I think you can figure out on your own from here with all the knowledge you have. I'll let you finish it. Good luck, and I hope the lesson helped. Go back and review whatever you need. Thanks for stopping by.